Okay, so just few announcements. So first is that the midterm grading has started. Hopefully, in a few days we should have the midterm done. Okay, and we'll hand it out with a sample solution and whatnot. For those of you who just walked in, as you know, lab is due today, but there's also homework out that you should take a look. The homework requires you to do some exercises on cloud, specifically Amazon's cloud. It requires that you have a free student account. Be sure to request credentials for your account or activate your account as soon as possible, because it takes a while sometimes for Amazon to approve a free student account. Okay, so keep those things in mind. Next week, there is going to be a guest lecture on Monday on IoT, sensors and things, pervasive computing. Okay, and then there is no class on Wednesday because I am away. So there's only one class next week, which is on Monday's class. Okay, there's going to be another guest lecture, another speaker who works on smart buildings and smart health will talk about how IoT can be used for interesting applications. Okay. All right. So we'll continue from where we left off last time. We started talking about fault tolerance. I introduced the notion of different types of faults you can see in the system, everything from a very simple crash fault where the system component simply fails, to Byzantine faults where the component has failed and it's producing arbitrary responses which could even be malicious responses. Right? And we are talking about how to deal with some of these things, and where we ended up with was this notion of Byzantine's generals problem, where I showed some examples that said to tolerate F faults where the nodes that are failing are Byzantine faulty, you essentially need 3F plus 1 nodes. Okay. That's a level of the degree of 3 replication that you will need. Okay. Much higher than crash faults where you just need F plus 1 replicas to tolerate F faults, which are F nodes that just fail, just crash but don't say anything if they have failed, because you need at least one node to be up and that node is producing the right response. So Byzantine fault tolerance is much more expensive to implement because you need 4 times or 3 times rather the amount of hardware to produce a system that can tolerate Byzantine fault. Okay. So 2/3, the reason you need that is you need 2/3 majority to eliminate the faulty process. Today we are going to also look at among other things a different technique to achieve agreement or consensus. Okay, in the presence of crash fault tolerance, not Byzantine fault tolerance, and we'll see that that actually needs 2 F plus 1 nodes to reach agreement or consensus, where nodes agree on something. Okay, but the nodes are not Byzantine; they are just failing silently. That's so. If you need Byzantine agreement, then you need 3 F plus 1 nodes. So we'll see crash fault tolerance is simply F plus 1. Consensus, and we look at Paxos today as an example of consensus, needs 2 F plus 1. Okay. Byzantine fault tolerance requires 3 F plus 1. It gives you agreement, but also allows you to tolerate malicious nodes that are doing arbitrary things in the system. So we will see this entire spectrum of failures and faults when we get to the end of the lecture. Okay, so basically now let's talk about agreement. So agreement essentially means that your nodes are agreeing on some result of a computation, and we'll look at examples of what that means. Now, as we said, essentially reaching agreement is not the same as just tolerating faults. Okay, tolerating faults simply says that some nodes are down, some nodes are up. In case of agreement, the nodes that are up or not faulty have to agree on the result of a computation. They have to say this is the right answer for whatever it is that they are doing. Okay. So that means that if just one node is up, it cannot actually agree with anyone else. You need more than one node for you to reach agreement by definition. Okay. So if you have only one failure, you would essentially at least need 2 F plus 1, so that 2 nodes are up that can talk and agree on what the result of a computation is. So that's something that you want to keep in mind as we move forward. Okay. So then before we talk about consensus and agreement, I do want to spend a few minutes talking about how network failures are handled. We only looked at node failures. Okay. But of course, there can be problems in the network as well, and there are a whole slew of techniques that have been developed to handle problems in the network, other than network partition or lost messages and so on. And we looked at some of this very briefly when we talked about RPC semantics. Okay. This is simply a summary of a slide that I had presented way back when we were talking about remote procedure calls. I said clients may fail, servers may fail, replies may fail, replies may get lost, responses may get lost, and you want RPCs to work despite all of those things. Okay. So, we will just pick it up from that point on, okay, and then talk a little bit about not RPCs, which we have spoken about already, but group communication. What can happen if messages get lost when you have group communication or multicast, where there is one sender, multiple receivers. Okay. In unicast, if a unicast is just two nodes that are talking to one another, we just assume your TCP. Okay. TCP is dealing with, I send a packet, I have a timeout. Okay. If I don't get an acknowledgement for that packet, I retransmit that packet. So, I keep doing this until I get an acknowledgement. So, I can deal with network failures. Eventually, if the network is up and the message gets through, you are good. Okay. Now, problems get more complicated if, rather than having two nodes talking to one another, you have n nodes talking as a group, where you have one sender and multiple receivers. That problem is called multicast. Okay. And one question you could ask is, how do you do this reliably? Okay. So, you can think about how you will generalize TCP. So, like in the case of TCP, your one sender, it sends a request, not a request, a packet. Right. So, it goes out to n other nodes in the system. It could wait for acknowledgements. Okay. If you don't receive acknowledgements from some nodes, you could retransmit that packet. That is a very simple generalization of TCP. Now, you have multiple ACKs coming, and you can track who is ACKed and who is not ACKed, and you have a timeout, and if some nodes are not ACKed, you can retransmit. So, you can do that. Okay. Now, the problem arises when the multicast group is actually very large. Let us say there are 10,000 nodes in this group. So, it is one sender. Okay. Every packet that you are going to send, you are going to require 10,000 packets coming back in the form of acknowledgements. Okay, that is not very scalable. As that group size grows, every packet requires a lot more overhead just to make sure the packet has reached lots of recipients in the group. Is that clear? Okay. So, then the question is, how are you going to build reliable multicast without having this problem of lots of acknowledgement? This is called ACK explosion problem, because the number of acknowledgements keeps growing as you send a packet. Okay. So, what could we do that will address some of these issues? Any thoughts? Yes.
Continue to send, but like at the receiver part, it doesn't receive the previous message, but he receives the current message. It knows that there is a message that is lost.
Okay. So, that is a good suggestion, and that will actually show you what is being done in the example here. Is we will not use traditional acknowledgements. Okay. What we will do is the sender will continue to send, okay, and leave it to the receiver to figure out that some packet has actually gotten lost. So, if I receive packet I and then I receive packet I plus 2, okay, we will assume packets are numbered. Right. So, I know that I am missing I plus 1, because I received a packet, I received another packet, and I see a gap between those two packets. Okay. So, in this case, the receiver can send a message back to the sender saying I lost some packets. Okay. This is actually called a NAC, a negative acknowledgement. Rather than sending an ACK, which says ACK essentially says I received your packet. A NAC essentially says I did not receive a certain packet. Okay. So, we can use this notion of a NAC, and basically what we have now done is we still get reliability, okay, but except that you only receive a message from a recipient if they have not received a packet. If they have received packet successfully, they do nothing. Okay. So, this is going to be more scalable, as we'll see here. Okay. So, you see an example here where there is a sender, there are 4 receivers. You essentially send out packet number 25. Okay. So, it goes out to all of them, and you will see that there are 4, in this case not 4, rather 3 ACKs coming back, and there is a missing packet there, which is not going to be. So, if that is the regular acknowledgement based scheme. Here is the NAC based scheme where the receiver is going to say, I did not receive a packet, I see a gap, and I actually send an acknowledgement back. In this case, you will see that the NAC can also go to neighbors, doesn't have to actually go all the way to the sender. If a neighbor still has that packet buffered, you can send it. You don't have to broadcast it to everyone. You can send it to the sender and some nearby nodes if you want to get that missing packet quickly. Okay, yes, question.
So what if the message is out of order?
Okay, good question. What if the message is out of order? Then this scheme will obviously not going to work, right? So you have to assume that this is first in order delivery of packets. If you essentially deliver packets out of order, you cannot use a NAC based scheme. You have to go back to an ACK based scheme. Okay? So, but you can think of TCP being an in order delivery scheme. So if you assume that the sender has n TCP sockets and is just sending out TCP messages, okay, they will get them in order. That's just a very simple example. You don't have to use TCP, just to show that there are many schemes that will do in order. But it's a good point. If you're receiving messages out of order, NAC schemes won't work. Yes.
Can't you just buffer for some amount of time and say, don't deliver until?
Yes. So question is, or not the question, the suggestion is, if you have out of order, can you use buffering and then use NACs and so on? You could certainly do that, okay, but you will not actually know exactly when the packets are received and so on, right? Because there's no time delay on on how long it takes. So I could buffer it, but if there is a gap, how long should I wait? It's not clear. In a NAC based scheme, if I'm assuming in order delivery, I got packet 10 and then I get packet 12, I know that I'm missing 11 because there is no delay or no timeout needed in that case. Right? So that will work regardless of network delays. A buffer based scheme will have to assume some maximum delay and some timeouts, okay, which can also be done, but that's one way to deal with that. Yes.
If I use an ACK-based scheme, I can possibly batch acknowledgement.
Yes. So point is, so what you're suggesting is, rather than sending lots of acknowledgements, I could batch them. I could ACK every 10th packet and say I received the previous 10. Certainly you could do that. Everything you're saying has been tried. Okay, but I mean, but still, if you're 10,000 nodes, I might still every n packets I get 10,000 ACKs. In a NAC-based scheme, if by and large the network is doing its job, you will get much fewer NACs coming back, so it will be strictly more efficient. If the network is extremely lossy, you are going to get lots of NACs, and then you have a problem, right? So it's all trade-offs of what the network does and so on. Yes, question.
What if the receiver receives the message, it reports to be missed?
What if the receiver receives a message that it has reported it's missed? Is that your question? So if you had in order delivery, right? So if you receive packet I and then you receive packet I plus 2, you should have, because the network is delivering them in order, you're not going to get packet I plus 1 at a later time. It is lost because you should have received it, because the guarantee is that you're getting them in order. The scenario you described, which is I have essentially sent a NAC for a packet and I get it because it just took longer, will occur if it is out of order delivery and just that the network was slow. But retransmissions are okay. Just because you got a packet twice, I mean, that happens in TCP as well, because you are actually keeping packet numbers. So you say, I got this packet twice and I throw out the second copy. That's not a problem, okay, because your packets are sequence numbers on them. This question.
So in practice, this probably will work really well with local networks, small networks. You're assuming in order and not lost the connection.
Right. The question. Yeah. So the question that's being asked is, does this only work across LANs? Does it work across internet? Okay. The answer is, it depends. There is a protocol called IP multicast that takes TCP IP, which is unicast, and makes it multicast, that is designed to work over wide area, except that it has not actually been deployed anywhere because it makes the router stateful, and our internet design principle says don't keep state inside the network. So it never actually got deployed. So what I'm saying is, technically it can be done, but there is no real deployments of IP multicast. When you're trying to do multicast on the internet, you do essentially do it as overlays, do it at the application level. So they're called application level multicast as opposed to network level multicast. In a LAN, you can still have multicast. You can do multicast on your home network, for example, because that's just a LAN based scheme. It doesn't require you to go on a WAN. Yes.
Are there any protocols apart from TCP that guarantee in-order delivery?
You're asking, are there protocols other than TCP that do in-order delivery?
You need it for the
Yeah. So
case that you use TCP, it doesn't get extended.
So there are many protocols that were developed, of course. There are many networking stacks, but the only one that has really become pervasive is the TCP IP stack. But there are other protocols. If you go back and look at the literature, you will see at one point there were many competing network protocol stacks. But eventually TCP is what has become the standard. And many of them did have similar properties in order delivery and so on. Okay.
But without acknowledgements or without a great amount of acknowledgements that would save anything compared to the middle case.
Right. So that's a good question. I mean, how do acknowledgements work and so on? I should also mention incidentally, TCP gives you the abstraction of in-order delivery to the application. Right? At the network level, things will arrive out of order. So you will actually buffer at the OS and make sure that you have a sequence of packets that are being delivered in order to the application. At the OS level, packets may arrive out of order because IP makes no guarantee that packets will actually arrive in order. They might take different routes as well. Right? That's something you want to keep in mind. So the abstraction is only from application standpoint, everything looks like it's coming in order. And then TCP and buffering is going to take care of it. So going back to RAG-based scheme, there are many variants of this. You can combine them and do have other variants as well. So there are lots of different possibilities on how you can do this. Okay. Okay. So coming back to application level things and so on, we can now think of multicast being done more of an application level rather than a network level. It's implemented using libraries. And when you do this, you can provide other properties, not just things like in-order delivery that you can use buffering and so on. We'll look at one specific one today, which is called atomic multicast. Okay? So atomic multicast says a sender has sent a packet and it's going to n receivers. Okay? You want to provide atomic guarantees. Either that packet is received by everyone in the group or no one at all. You don't want a scenario where I send it out, 3 of the 5 have received it and 2 have not received it. Okay? And you can, when I say receive, I mean you can assume that it will be retransmitted and so on. Eventually either everybody receives it or nobody receives it. That's the property we want to guarantee. Okay? And the reason this is actually interesting is we will have things like replicated databases. If you remember, you send a query, a transaction query. Okay? And it will basically send it out as RPCs to 2 database replicas. Either you want both of them to receive it, or you want neither of them to receive it, because you don't want a transaction to be performed on one replica but not the other. So from a networking standpoint, you want to have that guarantee saying if I do a send, everyone in the group gets it or nobody gets it, and you want a network to give you the guarantee. Okay? That problem is called atomic multicast, where it's all or nothing. You are getting the transaction like semantics, but now from a network. A send comes with an atomic guarantee, saying either it will succeed for everyone you send it to, or it will not be delivered at all. You will basically delete it from all OS buffers so nobody gets it. Okay. Now, there are many approaches that have been designed on how to do this. I'm not going to go into a lot of detail, but there's a picture here that explains the higher level concept. Okay. The higher level concept is one of where you are going to give a group view. Okay, where group view says what are the current set of nodes in my group. Okay, that's your multicast group. Okay. Let's assume that you are going to use something like TCP so that it's not the network problem. Okay, assume that if the nodes are up and the network is up, they all get it. Okay. The problem of atomicity will come when there are node failures. Okay. The reason we are talking about this is because fault tolerance plays a role. Okay. What if the message actually reached all the machines, but at least one process that was supposed to receive it has crashed? Okay. You have to detect that, and you have to say now that the process has crashed, I cannot give you the all guarantee anymore, because I cannot deliver it to that process. By definition, it's not up. Okay. So then I got to remove that message from everyone else's queue and say nobody gets this message. It's going to be the nothing case. Okay. So you want to essentially, when you provide atomic multicast, you have to think about not just network dropping packets, but you also want to think about processes crashing, because reliability or fault tolerance can happen, issues can happen both in the network and at the nodes. So what this is showing is Here's a case where P2 sent a message, the group was P1, P2, P3, P4, all 4 nodes are up, and the message has reached everyone successfully. So this is the everyone got that message case. Okay. Here's another case where essentially you are sending a message, P3 is sending a message, but the sender has actually crashed in the midst of sending the message, which can also happen. So the message has gone to 2 of the 3 nodes, and the 3rd node, before it could even send it, it crashed. Okay. So you cannot actually deliver this message anymore because it has not been received by anyone, not anyone, some nodes. Okay. So you have to have your system detect that process crashed and say, this message should not be delivered to other nodes in the system. Okay. So this is called detecting failures. It's called a view change. You say, has the group actually changed because some nodes have crashed? Okay. If the group has changed, then you basically essentially make sure none of the messages that were in transit actually get delivered. You form a new group. You will see a new group got formed, P1, P2, P4, saying the multicast group has changed. If the higher level application says, okay, I can still continue to function with that group, you can then restart the computation saying, we know that one node has failed. This is the new group. So the atomic multicast now works over this group. But if you need that node to be up, you can just wait for the recovery or whatever else you need to do. Right? But what it is guaranteeing is a safety property where you will not deliver a packet to a node when the node has experienced failure or the sender has experienced failure. So this is called atomic multicast. There are many libraries that actually do this. There's one called ISIS. There's an example or case study in the book which shows that was developed as a research project, incidentally, at Cornell University, okay, about 20 years ago now. And that basically implements all sorts of techniques to detect when network drops packets, when processes crash, when the sender crashes. All of these are actually detected by the library, and it makes sure that you get your all or nothing guarantees. Okay. So I just want to say that I will not go into details of ISIS, or the term is a little bit unfortunate, but that is what it is. So I think we'll continue our discussion of distributed all or nothing guarantees, but try to generalize that and look at it more broadly. Right? So atomic multicast is essentially a special case of a more general all or nothing property that we want, which is something like distributed commit. Okay. So you can think of distributed commit as a way to implement transaction like properties, saying it can be any operation, not just the sending of a packet. I either want all the operations to succeed on, not all, I either want that operation to succeed on all the replicas, or I don't want it to have taken place on any of the replicas. In case of atomic multicast, that operation was the sending or the delivery of a message. Okay. When we did transaction, that operation was the committing of a transaction. Okay. But it could be anything else. Okay. So you can think of, I want is all or nothing guarantees to work for many different operations. Yes, question. Okay. Question is how. Yes, the question is how does this differ from a distributed snapshot? So distributed snapshot is a way to have all of the nodes save their state, okay, in a consistent way. Okay. Yes, but yes, you are right. I mean, but in the specific case of distributed snapshot, we are taking a snapshot and we are storing it to disk. Now think of some other operation. I want all my replicas to perform a computation. I say what's 2 plus 2? Okay. Everybody has to do, that's a bad example. Let's say I want every node to append some value to a log or a database. Either everybody does it or nobody does it. So we want to ensure consistency of that sort. So how do you do this in a more general case is what we are going to see. So we are going to layer a protocol on top of any operation. Now what the operation is no longer our concern. We want to know whether all of the nodes have done it and agreed to do it, or we say nobody does it. Okay. Does that answer your question? I'm not sure that I fully understood what you were asking.
I'm just wondering, the approach that we use for distributed snapshot seems like should work for distributed commit as well.
Okay. Now I understand your question. Okay. So you are asking the approach that you use in distributed snapshot should work in distributed commit. the big difference between distributed snapshot and here is we did not assume there were failures of a node, okay, when we are taking a distributed snapshot. Here we want it to work even in the presence of failures. You understand the main difference? I mean, we did not consider fault tolerance when we were taking snapshot, right? We did not say should the snapshot succeed, not succeed in the presence of failure. Here we are going to look at the reason we are doing this is we are concerned about failures. If there's no failures, things are relatively simple, but failures is where the problem arises, right? So we want all or nothing operations for a group of processes, and we look at distributed commit as an example. Okay, again, this problem actually has come from the database world, just as you had transactions and so on. So some of the earlier proper techniques we are going to see come directly from databases. We'll see two-phase commit. Okay, it was proposed by Jim Gray, who was a very well-known database researcher, okay, at the time. We'll say three-phase commit also came from databases. Okay. Then we'll generalize it. We'll see Paxos. That basically generalizes this idea, saying how do you do this more broadly when there are broader class of failures. That came from the distributed systems community. Okay. Specifically, people like Leslie Lamport are the ones who have proposed things like Paxos. Okay. But we will go through some simple protocols first, then we will get to Paxos towards the end of the class. Okay. So let's start with two-phase commit. So what is the problem we are trying to do? We want a group of processes to all agree to either perform the operation or not perform it at all. In this case, it's commit. Okay. So we are going to say either everybody commits a transaction or nobody commits a transaction. This came up when we were talking about distributed databases. We said there are sub-transactions that are occurring in replicas. Okay. We don't want a case where some sub-transactions commit but others don't commit. Then as a whole, the transaction itself doesn't make any sense. So either they will all commit or they will all abort. So we want that property. Okay. How do we get a group of processes to decide whether they should all commit or they should all abort? That's the simple question. Okay. So what would we do? Okay. How would we go about solving this problem? The simple thing is we'll just ask everyone, what would you like to do? We'll get them to actually vote. Okay. If they all agree saying let's all commit, then we are done. Okay. In this case, if abort is like a veto. If any one process says let's abort, then we basically says the vote actually means everybody should abort, because if one process had some problem and wants to abort the transaction, everyone should abort the transaction. Okay. But if everyone successfully finished whatever they were doing and they all agree to commit, then we basically go ahead and commit. Okay. That's the simple idea. Okay. The way two-phase commit works is it's basically going to use two rounds that include this voting. Okay. So we'll pick a coordinator node. Okay. The coordinator node is essentially going to send out a request saying what should we do for this transaction, okay, and get responses. Every node is supposed to vote either commit or abort. It can pick one of two, saying I want to commit or I want to abort. You get back all the responses. Okay. And then you say, what did the vote say? If everyone has said commit, then the coordinator is going to send another message to all the nodes saying time to commit. Okay, that was the result of the vote. If any node said abort, then you are going to tell everyone to abort. Okay, that's basically what two-phase commit is. Okay, your question, yes.
It doesn't seem like it guarantees it to be atomic commit, because
Yes.
after the decision phase where you say commit, they can crash.
Yes. So the question being asked is, how is this fault tolerant? What happens if some node fails? And that is exactly what we have to analyze. Okay, let me go through this, then we'll say what happens if this node fails or some other node fails, and then we'll say it still works. Okay, so your question is.
So if some node fails, coordinator will know that like the second acknowledgement of I committed does not so the coordinator will not receive that message. So
Yes.
it will retry like after some time.
Right. So let's go through the protocol of two-phase commit, and then we will see exactly what you're saying. What if the node fails? What if the coordinator fails? And at different points in the phase of two phases, if there are failures, right? So so the way you understand this is these are the two state transition diagrams of the coordinator and a node. Okay? So initially you start with the init state, saying I am going to basically start off this voting phase. Okay? and then you are going to send a message. You're going to send a vote request message. Vote request is vote what you want to do, and then the coordinator goes into a wait stage where it's waiting for replies to come back. Okay, and then the replies, let's say replies do come back. If anyone has voted to abort, you are going to send a global abort message, and you move into the abort state, saying that the decision is to abort. If everyone votes commit, you are going to send a global commit to all the processes, and the decision is to commit. Okay? That's the coordinator state transition diagram. Here is what each node is going to do. Okay? Remember that the coordinator itself will also be a node, because you just pick the coordinator, so it is also gets to vote. So when it's voting, it basically is going to use this state transition diagram. The coordinator part of that node will do this. Okay? So initially, you are waiting to be asked what to do. Okay? When you get a vote request, you can decide one of two things: abort or commit. If you voted to abort, you can directly go to abort. You don't have to wait for the results of the vote, because you know that the coordinator will actually ask you to abort. However, if you voted to commit, you go into a ready phase, okay, ready state, and wait for the coordinator to tell you what to do, because you don't know how everyone else voted. Just because you want to commit doesn't mean that everyone else would have done so as well. So you go into the ready state and you wait to hear. Okay, the coordinator might either send you a global abort if somebody else voted to abort, and then you send an ACK and you abort, or it might send you a global commit, in which case you go into commit. Okay? So that's the same technique I mentioned, but seen through the view of a formal state transition diagram. Okay? Now here is where you can now start asking questions about what if something failed, and what if something failed at this point and this other point, and you got to analyze this protocol and say no matter what happens, bad things are not going to happen. And the bad thing in this case mean that some nodes have gone to commit and some nodes have ended up in abort. That we don't want to happen. Okay? So either we want everyone to be in commit or everyone to be in abort phase. Okay? That's the analysis we are now going to do. But before we do that, you have to understand what this two-phase commit is actually doing. Is this clear? It's a very simple protocol. Okay? And you will see that the messages are shown there in a time diagram where you ask what to do, go into ready state, and you either commit and get an acknowledgement. Okay, there is also pseudocode in the book, which I'm going to ignore here, because we are just going to ask what happens if some of the nodes fail. Okay. So let me ask some let's take some simple scenarios. Okay. Let's first take node failures, not coordinator failure. Okay. So let us say that a node has actually sent out its votes, it's waiting in the ready state, and it crashes. Okay. So then you can say, is this going to prevent the system from making progress? Okay, so you are in the ready state and one node crashes. What does this tell you about the system? Okay, if you are in the ready state, it should tell you that you actually sent your vote to the coordinator. Because at least specifically you sent a commit request to the coordinator. That's the only way you can enter into the ready state. Okay. Now, if you are the only node that has crashed and you sent your vote, okay, the coordinator will receive your vote, okay, and then it will presumably receive votes from everyone else, and it will make a decision whether to commit or abort. Okay, and the other nodes might actually go into either a commit state or an abort state. Okay. Now, when this node recovers, it still hasn't actually decided what to do, because it's still stuck in the ready state. Is this clear? What scenario we are talking about? So it has to make a decision what to do. In this case, you can actually ask another node saying, what was the result of the vote? Did you commit or abort this transaction? And depending on what this other node tells you, you can actually make the right transition, and you will still end up in the same state as everyone else. Is this clear, what I just said? Okay, basically you cast a vote and then the client crashed. Okay, so because you crashed, you can't hear from the coordinator what you should do, but other nodes will hear. Coordinator does not yet know your crash. Coordinator will collect the votes and send back a response to everyone else. Okay, just that you don't. The crashed node does not get that response because it crashed after it cast a vote. Okay, so everyone else will do whatever the coordinator asked it to do. This node basically got stuck in ready and then crashed. So when it comes back up, it can easily recover and figure out what is the right thing to do. and then it will do the same thing, whatever. The thing you cannot do is if you crash to come back and say, I crashed in the middle of the transaction, I should abort. That cannot be done, because you have to ask another node what the outcome of the voting was. Okay, so you can't do things like node crash, so let's just abort this transaction. Yes, question.
Does that kind of imply that you have to keep your state of what the transaction was so that you know to commit it?
Yes. The question is, does that mean that you got to keep state of what the transaction was so you can figure out later? Right. So like in any database, you got to write everything in a log. You can't keep anything in memory. We assume that if a process crashes, its log state will stay. Meaning it's the process that crashed. Okay, so when it comes back up, it can actually look at what this disk state was before it crashed. It will know there was a transaction in progress that was in two-phase commit state, and it will figure out where it was and so on. So all of these you have to actually log, which is why if you actually look at the pseudocode for all of this, you will see that basically everything is being written to a local log. You will see that write this to a local log. So when you come back up, you can see what has happened, and you can say I'm stuck in the ready state and so on. Okay, that's a good question. Is this clear? Now you can ask this question for any state. You can say, what if a process crashed while it was in the middle of init? It basically hasn't even voted, it basically crashed. Okay, what should you do? Right, so you can come back up. Okay, other nodes presumably have voted. Okay, the coordinator may have gotten their vote. Okay, the coordinator never heard from that process. Okay, but the coordinator may decide that since that process hasn't actually responded, maybe it is safe to abort. It's not safe to commit even if the other nodes have actually said you should commit, because this node has actually crashed without even casting a vote. So what if it had decided to abort? Then if you make the rest commit, then you are in a bad state. Okay? So it's safer to, in this case, just say I'm going to ask everyone to abort, even if the remaining nodes have voted to commit, because that is always safe. Okay? Because you can force everyone to abort for no reason at all. Okay, so this node, when it comes back up, it will probably see everyone else has aborted, so it can essentially make a direct transition to abort. Your question, yes? Okay, the question is, under what condition can you actually go from init to abort directly? This is only going to happen when you have received a request for a vote and you voted to abort. Because if you vote to abort, you know you are forcing the entire system into an abort. Okay? Why would a node abort the transaction? No. Oh, why would it abort the transaction? So the transaction can be aborted for any reason. There may be a write-write conflict on the transaction, because it's like a database transaction. Right? So you can, why you are going to abort is not a question we should ask here. We should say you did a transaction, you have the choice of committing or aborting. Maybe there were conflicts, maybe this is optimistic concurrency control and something went wrong in the transaction. So you want to abort the transaction. Right? So there may be any number of reasons why you may abort the transaction. The point is, assuming you have decided to abort, you are going to say, I will want to abort to the coordinator. In that case, it's okay to go to the abort state directly without waiting to hear for the results of the vote. Okay? Yes.
So one node fails, and then the coordinator can't do a global commit anymore. Does it stop the whole system?
Right.
Failure?
Okay. Question is, if one node fails, can the coordinator do a global commit? That's your question, right? So the answer to that question is depends on at what point in this two-phase commit it fails. We already looked as an example where that failed node has actually cast a vote, it's sitting and ready, and then it failed. In that case, you might still get to global commit, because if it voted to commit, everyone else voted to commit, the coordinator has everyone's vote. Okay? The vote, everybody's voted to commit. So you push the rest of the system into commit. When this node comes up, it's still stuck in ready. It's going to either ask the coordinator or the other node, what should we do? And then it will basically be told the result was to commit, it will go into commit.
Okay.
Right?
The second voting and the node is still down, can you decide to just continue, or do you?
Okay, that's a different question. The question is, if once you failed in the middle of a transaction, you can recover and see what to do. Now you are asking, while it's failed, can you do additional transactions? That depends on the what you want to do in the system. Should remaining n minus 1 replicas continue to process transactions, or do you want every node to do the transaction, and so on and so forth. Right? So that's orthogonal to just two-phase commit. That's higher level property what you want to do. So long as your strict majority, it may still be okay to proceed, for example. Right? So I think with that's okay. Yes.
So what if the coordinator broke down?
Yes, good question. Question is, what if the coordinator broke? I've been only talking about nodes failing. Okay, clearly coordinators can fail as well. This is where two-phase commit actually has trouble. Okay, if the coordinator fails in the midst of a voting, sometimes the entire system may be stuck. Okay, specifically, if the coordinator is stuck, let's say coordinator is asked for a vote, everyone voted to commit. Okay, and they are all in ready state. Okay, coordinator got the vote, but before it could transmit the results of the vote, it has crashed. Okay, then you should say, can the remaining node decide among themselves what to do? Is the question clear? Okay, so you asked for a vote, everyone, all the other nodes except the coordinator, okay, have voted to commit. They are all in the ready state, but the coordinator has never come back with the results of the vote because it crashed. So question is, what can the other nodes do? Okay. Yes.
We can't decide if the coordinator can still.
Yeah. So you could ask, you could say there are one of three things you could do. The rest of them can say, ask one another and say, we all voted to commit. Should we commit? Okay. This is actually not safe because the coordinator also node. Okay, it's not just a coordinator. So what if the coordinator itself, which is now crashed, had decided to abort? You can't do that. Okay. So you could say, okay, maybe then we can abort the transaction. Is that safe? Okay, we don't know what the coordinator did. You can say, let's go ahead and abort. That's also not safe. The reason is the coordinator is also a node. Everyone has voted to commit the transaction. What if the coordinator has, in the midst of sending out the vote, sent the vote to itself and it committed, but the vote never got to the rest? So that node has committed, but the rest of the node never got the results of the vote. So when the coordinator comes back up, it has actually committed the transaction because it is a node and a coordinator at the same time. Right? So you can't do that either. Right? So what's the third alternative? Is to wait. Wait for the coordinator to come back up and tell you something. If the coordinator does not come back up, you are deadlocked. You can't make progress. Okay? This is the problem with two-phase commit, is under certain scenarios, if the coordinator crashes, especially when everyone has voted and is ready state, there is no progress. You cannot guarantee a liveness property. Liveness means you make progress. There is safety property. Safety property is saying that nothing bad is happening. You are stuck in ready. You are not deciding on anything. Okay, so nothing bad has yet happened, but you can't do anything either. You are completely stuck. Okay? So this is a problem with two-phase commit, okay, which is it has safety properties. We will see that you can analyze all these different scenarios. You will see that bad things are not going to happen. Okay, but it will also have coordinator crashes are going to block the system. Good things cannot happen. Yes, question.
Each vote just have an expiry time allotted to it or something of that nature? I mean, I guess that brings in the whole time synchronization issue.
Right. The question is, can vote have expiration time? It could, but the problem I mentioned is not going to go away. Right? So in this particular, this is the most thorny problem with two-phase commit, where everyone has sent their vote to the coordinator. Okay, and the coordinator has processed the vote, but it has crashed before it could relay the vote to everyone else. But perhaps because it is a node itself, okay, if that vote has actually been relayed to the local process on that node and it has committed the transaction, this expiration is not going to help any other node. They cannot make a decision. You can't say that time expired, let's all abort, because the crashed node could have committed before.
Supposing if the coordinator crashed, but then like eventually came back and then was about to commit it, it could then see, like assuming that that happened after the point of the timeout, when the others decided to abort, then it would see that it's been enough time to decide to abort.
Right. So you are saying, what if the coordinator crashed before it could relay the vote to anyone, including itself. Okay, and others have decided to abort. In that case, when you come back up, you can actually ask the others and abort. But the problem is you are not guaranteed that it will only crash at that point. What if it has actually caused itself to commit, but it hasn't told the others? Okay, because we don't actually know how long messages take to propagate and so on. Right? So in that case, you cannot assume that and abort. That is unsafe to do. Okay, yes, question. Yes, this is a single point of failure. That is why we are going to get to Paxos, where we'll try to get around some of these. Right? But there is a solution to this problem, which is to generalize it. I'm not going to go into all of that pseudocode. You can look at it. It basically says what I said with kind of pseudocode in there. This is just various scenarios. What if the node is in commit and is what should you do and so on. We talked about some of the more important cases, but there are a few others that I didn't talk about. Instead, what I'm going to show you is a generalization of two-phase commit, which is called three-phase commit. Okay. Three-phase commit, you add one more state to the system, which allows us to deal with coordinator crashes. Okay. It will still have other problems, as we will see. Okay. But at least coordinator crash, this problem of everyone is stuck in ready and cannot make progress is going to go away. Okay. What we are going to do is we are going to add a state between the wait state and the commit state. We are going to add a pre-commit state. Okay. So we are going to have 3 rounds of voting, which is why that's called, well, not 3 rounds of voting, 3-phase protocol, 3-round protocol, just to get around some of these issues. So in first stage, you ask for everyone to vote. That's round 1. Okay. And then if any one node has actually voted to abort, in the next state you say everyone can abort. Okay, so that is not going to change. But if everyone has voted to commit, commit is going to be done in 2 steps. You are going to tell every node saying the results of the vote is in commit, go to a pre-commit state and wait. Okay, so everyone says, okay, we are going to commit, but they have not yet committed. They're still sitting in pre-commit state. Okay. Once everyone has actually acknowledged that they are in pre-commit state to the coordinator, it is going to say, go ahead, please commit, and then everyone actually moves to commit. Okay. So here is basically what is going to happen. So you are going to do commit in 2 steps. Okay. Now, how does this help us with the coordinator crash problem? The same problem. Everything else is the same. Whatever we talked about earlier in terms of you crash when you are a node, you are in it, you are in ready, all of that is still the same. The only thing that is actually changed is we added this pre-commit step. Okay. So now let's take the same case. Okay, you asked for a vote. Okay. You basically got all the coordinator got all the responses, but the results of the vote has actually not come back to you. Okay. So everyone is stuck in ready. Okay. Everyone except the coordinator, which has crashed, is stuck in ready. Okay. So in this case, the remaining nodes can still actually make a transition to the abort state, and that's still going to be safe. And the reason for that is at most, because no one has heard from the coordinator, okay, it has essentially gotten the votes, and the worst that could have happened is it's told itself, I'm going to commit, and put itself in a pre-commit state, but not told anyone else. Okay. So at most what would have happened is it has itself gone to pre-commit, the coordinator, and then everyone else is stuck in ready because they don't know anything. Okay. Since that node is still in pre-commit, if it comes back up, you can still tell it the decision was actually made by everyone else to abort, and you can abort. Okay. In 2-phase commit, if it has actually committed, there is no undoing a commit. You already committed the transaction. Because you can undo a pre-commit, but you cannot undo a commit. Is this clear? Okay, so this is basically adding one step to make sure that we are going to decide on something, but let's not do it yet. Okay. Yes, question. Yes. So the transition. So question is, should there be a transition from pre-commit to abort? That's shown in the failure case, is not actually shown here, right? But because we don't show what happens in the case of failure, etc. Is that clear? What I just said? Why you will not be stuck? Because you are not going. You are going to commit in 2 steps. At most, if the coordinator crashes after the vote, you are still stuck in pre-commit. You are not in commit. So after the voting phase, you are either in abort or in pre-commit. Okay, from pre-commit, you can still undo whatever you did. Okay, so and you can still ask all sorts of questions saying, what if I received, let's say I'm a node, I got a request to go into pre-commit, I crashed. I never got the final commit message. Okay, you come back up. Okay, you can always still ask everyone else saying what happened. Most likely from pre-commit you only go to commit. So you will say commit the transaction and then you will commit. Or if something else happened, yes, question.
So one issue that I see is if you, as a client, send your ready request and then crash. And
So you crash here in ready, right?
crash and ready, but you've already sent your response to the server.
Yes. So ready, you send your response and then you go into ready. That's basically what the transition is. Always if you're in ready, you already sent the vote. Okay, so you'll see that before you go in, you do something and then you make a transition. So if you're in ready, you have voted to commit. You don't know what anyone else has voted, but you voted to commit, you are in ready. Okay, so if you come back up, you can still decide to commit or abort depending on what everyone else did. Is this clear? Yes, question.
So if you crash after you're ready as a node, and then you came back up and you received the global commit message, would you just switch directly from ready to commit?
Right. So the question is, if you crashed after you're in ready and you essentially right. So you probably, the answer is you will not get a global commit because you did not act a pre-commit. So in most likely what would have happened is the coordinator would have timed out saying nobody is replying, but it's safe to abort the message. I mean abort in that case because you yes, 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 because you don't want to jump 2 steps if you haven't voted what to do or acknowledged that you are in pre-commit. Okay. So I mean you will see that when you start thinking of failure cases, you got to think of all possibilities and make sure that regardless of what happens, you have actually a safe way to make sure everybody commits or everybody aborts. Okay. So it is more complicated than it looks. This looks pretty straightforward. If you say I have 3 steps, this is what the steps are, all that sounds good. But when you start saying what happens if I fail in this state and everybody else has done that, and so how do you do it? You have to start reasoning about it. It gets pretty complicated very quickly. Okay, but you will see if you analyze it carefully, you are going to essentially get the properties I mentioned, where you are not going to block if the coordinator fails. Okay. All right. So with that, I'm going to switch gears and then generalize. There are still issues with 3-phase commit. We will talk about them in just a moment, and we'll see how to generalize them and think about broadly this notion of agreement and consensus and so on. Okay, but I do want to go back to this issue of replication and fault tolerance. Yeah, remember that we have used replication for multiple purposes in this course. Okay. One reason to replicate is you want more performance. Okay. In that case, so think of a replicated web server. A request comes in or requests are coming in and each request is sent to one replica. You're splitting the load across multiple replicas. Okay. That is replication to get better performance, to scale your system. In the kinds of techniques we have been talking about now, replication is being used to achieve fault tolerance. Every request is being sent to all the replicas. They all perform the computation and then they vote using 2-phase commit or 3-phase commit and so on. Okay, so in this case, you are not getting scalability, but you are getting things like fault tolerance. Okay, so you have to keep both of these things in mind. Okay, so we are in this category where each request is sent to all the replicas, and you are going to vote, and you are going to either do BFT, you are going to do 2-phase commit, 3-phase commit, and we'll see Paxos in just a moment. Okay, so when you are thinking about doing this for performance, you are going to split the incoming request across replica. Okay, each request is processed by only one replica. There is no fault tolerance there for that request. Okay, of course, if the node crashes, you can say other nodes are going to start receiving the remaining requests, but that request is gone. Okay, it's kind of no, it's going to fail. But other requests will get repartitioned, and you can still continue to function. Okay, so these are all things you want to keep in mind. But let's move on to the next thing we want to talk about, which is consensus. Okay. So consensus, you will hear the word consensus and agreement. Okay. They are somewhat related. Okay. In this case, we are not going to distinguish them too much. Essentially, what you want is to agree on something. Okay. in case of 2-phase commit or 3-phase commit, we were trying to get agreement on should we commit the transaction or should we abort the transaction. Everybody had to agree and perform that same step. Okay. But you may be wanting to agree on anything. Right? You might say, I send a request, a computation, and I want to agree on the response of that computation. Okay. And so long as everybody agrees, I say that's the right thing to do. Okay. So agreement has to go beyond just distributed commit. So we are generalizing commit to say that was just a type of agreement. Now we want to get agreement for any computation we want to perform. You send the request to all of them. They all perform a computation. They all produce answers. You want to somehow vote and figure out what is the right answer. Okay. And if you get that, if you successfully manage to get a result of the vote, you essentially got an agreement. Okay. So there are many terms we'll talk about when we talk about consent. Agreement is every correct process agrees on the same value. Termination says that that is actually that process of voting and figuring out the correct value will actually terminate. 2-phase commit did not have termination property. If the coordinator failed, you could not terminate that commit. You would actually be stuck. You couldn't agree there. Okay. So we want that property as well. 3-phase commit did a little bit of that, but we'll see that it can tolerate process failures but not network failures. Okay. The validity says if all nodes actually come up with the same answer, then we all agree on that answer. Okay, you want agreement, but you also want to agree on the right answer. Okay, because otherwise agreement is trivial. You will say every time you ask me a question, the answer is no. Okay, we just don't perform any computation. That's a trivial way to get agreement. Okay, but not really a useful way to get agreement. We want to get the right answer as well. So it says if you compute the right answer, you want to actually agree on that right answer. Okay, integrity says you want that's basically the related to agreement, saying you at most essentially agree on one value. Okay, so and then somebody should have actually computed that value. So these are all properties, just as your ACID properties for transactions or consensus protocols. You want to have agreement property, termination, validity, integrity, and so on. We are really going to focus on the first one, but the others are kind of in the mix when we talk about Paxos and so on. Any questions on this? Okay. So now let's talk about problems with 2-phase and 3-phase commit. Okay. In everything we have talked about so far, we assume that processes can fail. A node can fail, a coordinator can fail. We did not worry about the network failing. Okay. So you can think about network just got partitioned. There are some nodes on the left half that the network is broken into 2 pieces. I just cut a link. Okay, that caused my network to split into 2. The network is still functioning on the two sides. Okay, there are nodes on the left side that can talk to one another, but they cannot communicate to any nodes on the right side. There are nodes on the right that can talk to one another. They cannot essentially talk to the other nodes. Okay. Now, in this case, your 2-phase, 3-phase commit won't work by definition because everyone has to vote. Right? You want everyone to vote. And if you cannot talk across a network partition, how are the messages going to go back and forth? Right? So by definition, these things are not going to work in presence of network partition. Okay? But if you still want agreement, we are going to change the definition, saying not everyone, but if a majority agrees, we can still make things work. So if you cut the network into 2, either the left half or the right half is going to have a majority of the nodes, assuming it was not even, for example. Right? If you have 4 nodes and you break it in 2, you have 2 and 2, that's not majority, but let's assume that does not happen. Okay, so if you have a majority on any one side, you want those majority to continue to decide this is what we are going to do, because the majority have agreed that 2 plus 2 is 4, for example, or the answer is to this transaction is such and such. Okay. So this is going to give us consensus protocols. Consensus protocols work with majority. 2-phase and 3-phase commit work with everyone voting on something. Is that clear? So if your majority agrees, you say that is the answer. I don't want everyone necessarily to vote. I want the majority to vote. Okay. So what this also says is they can also tolerate silent failures. Right? If some, not just network partitions, but some nodes simply fail, they crash, then the majority can still decide what to do. Okay. Failure of some minority of the node does not prevent me from making progress. Okay. So I can continue to make progress if a minority of nodes fail, if the network gets partitioned, and so on and so Okay, so it's a different way to think about things, but we are trying to essentially get majority vote. That's the thing you want to keep in mind. Okay, now the protocols we are going to look at right now, we'll assume that nodes are crash fault tolerant, but not Byzantine faulty. Okay, if you are Byzantine fault tolerant, you actually want BFT protocol, like what I was showing you when we talked about Byzantine general problem. Okay. Here, if you are a malicious node and you send bad answers, different bad answers to different nodes, you will not get everyone to agree. You will confuse everyone and you will not even know what to do in that case. Is that clear? Okay. And the simple reason that you can think of is the following. Let's say there are 3 nodes, A, B, and C. Okay. Let's say A is Byzantine faulty. Okay, so that's the bad node. Okay. Now, if A and B try to agree on something, it might send a bad, and A and C are trying to agree on something. Each of this is a majority group, okay, because 2 out of 3 is majority. But A could, if B and A say what's the result of 2 plus 2, A could say 5, okay, and B got 4, so they don't agree, so they can't make any progress. Okay. And you can do the same thing with C. Okay, you can tell C that 2 plus 2 is 5, and C will not be able to figure this out either. So only if B and C actually happen to talk to one another can you make progress. Okay. But if you try to have a faulty node in between, it can essentially give you bad answers and confuse things. So we are assuming there's no Byzantine faulty nodes, but nodes can crash. If A went down, okay, the only nodes that are left in this case is B and C, which is still a strict majority out of 3. 2 out of 3 is a majority, and then you can still make progress. So that's what we are assuming for consensus, not Byzantine answers, just either a right answer or no answer. Okay. So basic point is we want majority to participate, not all nodes, which is why we will get rid of some of the issues with the 2-phase and 3-phase commit. So it's again a simple voting based protocol, but it looks a lot more complicated when we see it, but we'll go through it. Okay, so you want the following properties. You want safety properties, okay, which means that all nodes should agree on the same value. Your majority of the nodes, they should all agree on the one value. Just as when you did distributed commit, everyone agreed to commit or they agreed to abort. Same thing here. The majority should agree on one value. Okay. Furthermore, that value should have been computed or proposed by a node, because as I said, a trivial way to get consensus, everybody agrees for whatever question you ask, the answer is no. Then I got a protocol. It's not a useful protocol, right? So you want to agree on a value, and that value is actually computed by someone. Okay. Liveness essentially says I'm going to make progress in spite of failures. So if a minority of the nodes fail, less than n over 2 nodes fail, the remaining nodes will still be able to reach agreement. They can still figure out how to make progress. Okay. The liveness is not guaranteed if nodes continue to fail while the protocol is trying to figure out what to do. Okay. So you might have to restart the protocol. If a node fails in the midst of deciding what to do, you will not reach agreement for that round, but you can restart the whole protocol and say now we have n minus 1, let's still agree, that's still a majority. Okay, because so long as you have more than half the nodes up, you are still okay. Okay. Now things get thorny when you try to deal with all sorts of problems. Network can get partitioned. Okay. You still have to make agreement. Leader can crash. This is like the coordinator crashing. Okay. Still have to get to agreement. Okay. In this case, you are going to just do a leader election, say new leader gets elected. That round is going to fail. We say that round didn't produce result, we'll elect a new leader. So long as majority of the nodes are up, you restart and ask everyone what to do. Okay. You might essentially have a new leader trying to propose something that the old leader had proposed before it crashed. You still want to make sure you agree on the right answer. Okay. You can have leader election where more than one leader gets elected. Okay. So you have a network partition. Left half elects a new leader. The right half actually has the old leader. They still continue to function. You don't want them to do bad things. Right? You don't want to say I'm the leader, so I'm going to agree X here and Y there. Okay, that's going to be a problem, because if you agree on something, nodes have to agree on the same thing. Okay? So despite of any of these issues occurring, you still want to reach consensus. Okay? And because the failure cases are problematic, you want to think of a scenario where it works regardless of all of those things. The only thing we are assuming cannot happen is nodes are Byzantine faulty. They are not producing bad malicious responses and causing the system to misbehave as a whole. Okay. But all of these other things can actually happen. Okay. So, I am going to quickly go, we have only 5 minutes left. So, I am going to show you a little bit of this and we will come back to this because there is a little more things we want to think about. Okay. So, this is a 3-phase protocol. Okay. And there are lots of sort of jargon here, but the basic idea is you basically have a leader. The leader is essentially going to say, I think the answer to the question is X. Okay, you say, what's 2 plus 2? Maybe that's the computation. Leader is going to say, I think it's 4. Do you agree or not? Okay. So, just as you in the 2-phase commit, you say, what shall we do? Do you agree to commit or abort? In this case, you are going to propose an answer and say, do you agree or not? Every node can agree or disagree, saying, I don't like your answer. Okay. Or you say, I agree with your answer. So, you can vote whatever you want. Okay. If majority says, I think 2 plus 2 is 4, the leader can say, fine, 2 plus 2 is 4. If a majority says, no, I don't agree, then you have to repeat. Okay. You have to say, okay, let's try something else. And then the nodes can also tell it what to propose if you so wish. But essentially, that's how you are going to go about this. Okay. You are going to have an answer, say, here's what I propose. If everybody agrees, then you are done. Not everybody. Majority agrees, you are done. If majority don't agree, then you are basically, and you don't have to wait for everyone to vote. That's the important part. You only want the majority to vote. This is why if nodes have failed, you can continue to make progress, because if the majority agrees, we are done. Okay, 51%, or 50 point whatever, some percent, majority of the nodes. So you know that the minority cannot outvote you. So you need essentially strict majority. Okay. That's the basic idea. And there are lots of details here, which I think we should come back to, because there are 3 phases and we need to understand how this works and what the properties are and so on. So I'll come back to Paxos next time. Right. So we can actually stop the class here today, because it's going to take a little longer to explain. Okay. So for those of you who came in late, Monday is a guest lecture on IoT. Okay. So interesting topic. Please make sure you come. Wednesday there is no class. Class on Wednesday is cancelled because I am away. Okay. So as a result, there's no office hours on Wednesday either. Okay. Something you want to keep in mind.